Okay, so all right, so finishing off part C of homework 3 for process dynamics and controls. Excuse my cat, I'm sorry. Um what we'd be doing is simulating a time response of the column in part B over another 300-second interval as the reflex ratios rank from 2 to 5 over 10 to 100 seconds. So we're essentially going to be modifying uh, uh, So gonna be working on this monitor, as you can see, but still have to type on my laptop. Um, but yeah, as you can see, we're gonna be kind of modifying this, and we'll see how kind of the reflux ratios that we modify change these moles and moles fractions, and how that kind of our constant line, that blue line right here, as you can see, how that kind of we have our moles kind of go over that, and it just causes the contrast of our mole and mole fractions to kind of differ. But let's go ahead and start this. So what we're going to be doing here is starting from Tn, we're going to be equal to 300, right? And we're going to be setting up a res2 solver IVP, which is essentially we're making a solve IVP function. Um, but we're gonna have to name it something else. So res2 equals solve underscore IVP. And this is going to be for our right hand side from 0 to Tn. So from 0 to Tn, and we're going to be using our res1 solver. So we just named that res in this case. So let's just keep it like that. So res y, and then to put in our brackets, res dot y. We have our bracket here, and this is going to be semicolon -1, I believe, comma -1, right? And then from here, we're going to add our method, which is redow equals redow, and our dense output is going to be equal to true, be equal to true. And our args, our argument in this case, is essentially going to be lambda. So let's do, so our arg is going to be equal to lambda. It's going to be equal to lambda from t to 3 times our ramp function of t from t to 10 to 100, right? We're changing these intervals here, and we're going to add a +2 here, and then close it. Okay, we go ahead and run all of this. I'm sure it's not going to work. Okay, so as you can see, I fixed that mistake. Our issue was I forgot to put a comma right here. So now that we have that done, we can go ahead and continue off with the rest of this code. Uh, Essentially what we're doing is changing this reflex ratio, right, and changing and modifying the solve IVP function. So one thing I want to do is I want to go up here, and I want to take this code right here. We can just modify this code, as you can see. So let's control C that. And what we're going to want to do is just change this to res2, right? We're working on res2 here, and let's go ahead and input this data right here. I don't believe we need to include the rest of the data. So let's just go ahead and paste this, and hopefully this is what we wanted to see. Shift into that. Nope. Oh, okay. So let's go ahead and input the rest of this. So I think that we need all of it. So yeah. All right. Perfect. So this is exactly what we want to see. Essentially what we're looking at here is, as you can see, we're stimulating a time response in the column over 300 seconds as we ramp up the reflux ratio from 2 to 5 over 10 to 100 seconds. So still uh yeah, so modifying this data right here from 10 to 100 seconds, um and ramping it up from 2 to 5. Okay. So as you can see here, we have all of these molar compositions. Really, the only difference, as you can see from this one and this one, is the molar compositions. Some of them actually go above the feed. So that entail just changes these compositions here, as you can see. But yeah, so let's go ahead and start with the next part of this, which is creating a series of 5 McCabe-Thiele diagrams. So as you can see here, we made one of these. However, we're going to make 5 of these, and we're going to be showing the time varying response of the column as the reflux ratio is increased. Okay, so let's go ahead and start with the code for this, see what we're looking at here. We're going to essentially want to be starting with creating again, a t-plot equal to np.linspace. And in this case, it's going to be from 0 to tn to 5 because we're creating uh, 5 plots essentially. Okay. So now that we have this, we can go ahead and define our x's, our mx's that we defined up here. Just kind of want to reference some of these points. No, we're going to be creating something. So mx's, sorry. And this is going to be equal to um, our res2 dot solve for our t-plot that we just defined. Okay. So now that we have that, we can go ahead and start by essentially kind of creating the subplot, but we're going to be modifying a lot of things still. So fig equals make underscore subplots. And then our rows are going to be equal to 1. Our columns are going to be equal to 5 in this case, because we're looking at 5 of these time plots essentially. And our subplots titles. So subplot underscore titles. Make sure I'm writing this right. Subplot. Ah, no, subplot underscore title. Yeah, subplot underscore titles is going to be equal to, so this is going to be equal to our f dot, oh, dot time. I did that right. And this is going to be equal to, yep, so that quotation is going to go towards the end. So f time, we're just essentially creating our subplot title. So f time is going to be equal to t semicolon from go ahead and pause this. Kind of getting stuck here. So yeah, I wanted to set this at zero point 0 for our decimal, and I wasn't exactly sure what the number was, but it is zero point 0 f. We're going to go ahead and continue the rest. So this is just going to be creating for what we're creating it for, which is essentially our t plot. So we can go ahead and do for t and t plot, and that should go ahead and finish that code. Okay. So now from here, what we want to do is essentially define what our x plot in this case is. So our x plot is going to be equal to np.linspace, similar to what we did for our t plot. And this one's going to be from 0 to 1 to 100, as we have been doing. Okay. So I believe we did identify that before. Not sure we had to still do it, but let's go ahead and then create these subplots. So fig equals make underscore subplots. Uh, Fig equals make underscore subplots. Yep, so fig equals make underscore subplots. Our rows are going to be equal to 1. And okay, so I went ahead and just moved my um move my screen over because it's kind of annoying looking back and forth. But um, let's go ahead and yeah, beat that up. But let me go ahead and let's move this down so it just easier to look at. Okay. Yeah, now it's a little weird because I'm looking at a small screen. But okay. So fig equals make underscore subplots. Our rows are equal to 1 and our columns are going to be equal to 5. Going to be equal to 5. And we can then create our subplot title. Wait, no, I was thinking we need to do it again, but no, we do not need to do that. So let's go ahead and create our X plot. Let's go ahead and set our for loop. So for I in range, let's do that first. So for I in range, our T plot size. Okay. So then we can set our M's and X's equal to NP dot split. MX's, yeah, so MX's. And then in our brackets, we can set this for our I, and then this will be 2. Okay. All right, so now what we can do is set our Y's, and this is going to be equal to Y equals alpha times our X's divided by 1 minus our X's plus alpha times XS times our X's. Okay. So now we can create our X steps and Y steps. So, let's go ahead and see if we can bring that down and just modify it a little bit. See how that does it. But let's go ahead and put this over here. Okay, so we have our X's. So this is going to be from our X's at 0. Um, and this is going to be np dot repeat for our X's again from 1 to -1 at 2 and our X's at -1. Okay, so just modifying that. And then our Y steps are going to be, oh, I think we need to change this one too. So just X's and then our Y steps is going to be np dot repeat and then our Y's. So it'll be the same thing. Okay. Dot size. Okay. Okay, so I realized I was still sharing my screen here, but I'm sure you could see my screen also here, but from the camera angle. Yeah, but sorry, I just changed the screen. But yeah, as we looked at, we created this for loop for our M's and X's. And again, we created our X steps and Y steps like we did before, but we just had to change our variables for our X's and Y's. Oh, forgot this again. I keep doing that and then pressing that again. Okay, so yeah, we're just changing these variables for our X steps and Y steps. So pretty similar. Okay, so essentially we're almost done here. What we're gonna want to do now is we can go ahead and actually we're gonna be creating our scatter plots. As you can see here, this is an example of one of them. I'm gonna go ahead and I'm gonna copy and paste the ones that we looked at over here. So these scatters, I'm gonna bring them all down and we're gonna see how we modify just a few of them. Okay, make this all indented the same. Okay, so some things we have x from 0 to 1, y from 0 to 1, we have our equilibrium one, x plots. We have the same equation. However, what we're going to want to do here now is create our rows and columns. So we have our rows, and this is just going to be equal to 1. However, our columns are going to be equal to I plus one. So essentially, this is just an iterative loop, and we're making sure that it kind of creates one for every single plot. So we can go ahead and do it for this one too. Let's go ahead and do that. Columns equals I plus one. Okay, so let's go ahead and do it for this one. Rows equals one, columns equals I plus one, just creating that loop. So for every single one of our time plots. And then this one, we're going to make 1200 for our width. And then our height, we'll just make it 400. And then the rest of this looks good. Okay, so let's go ahead and put this. Let's see. Hopefully we did not do something right. Um, MP dot split. Looks like we have all of our right quotations here. It's weird. MP dot split. Okay, so we did forget a comma, and that is right here. That's right here. So let's go ahead and shift enter this again. What happened here? Go ahead and run all of this. No, it's weird. Mode equals lines. We have our line colors. And okay, so I believe I messed up columns and I made this plural here. So let's try to see if this fixes our error. Okay, let's go ahead and shift enter this again. Okay, beautiful. So this is exactly we want to see. As you can see, we have our five t time plots. Let's go ahead and see how this kind of compares to our last one. Am I still sharing my screen? Oh my God. I got wait. Okay. Give me 1 second. I want to make sure I am still sharing my screen. It's weird because usually it has a line. It's like, okay, but now we have this one. Okay. All right, so we look good. Um, as you can see here, we have, okay, so this is still boring me. I don't know why I feel like I'm not sharing my screen. Hmm. Okay. Sorry about that. So we have our five time plots at time equals 0, time equals 75, time equals 150, time equals 225, and time equals 300. So essentially, we're creating this time response as we increase the reflux ratio. So as you can see, how each one kind of differs than the other. At time equals 0, we get closer, and then at time equals 300 is substantially different as well. So that kind of differentiates the two of them. But yeah, looks good.